Alrighty, folks, that was great. So we're moving on to the favorite part of the day for many of us, which is the lightning talks, which is, of course, right before the beer and gear. Alrighty, so we have 3 talks coming up. They're ranging about 10 minutes each. So Alberto is going to come up first, and then just want to make sure that Jeff and Mingwei are ready to go up in sequence after Alberto. Yeah. So forwards, backwards. Don't push those.
Okay. Wow, it's like a trap. Hello, everybody. I'm Alberto Inotti from CADA, UC San Diego. And this presentation is about an event that just ended less than 48 hours ago. It's the first BGP hackathon that we, CADA, hosted at the San Diego Supercomputing Center at UC San Diego. And it was, as I said, this past weekend. We organized it on purpose on this date because we wanted it to be just before NANOG in order to encourage participation to both events. Actually, a lot of attendees from the hackathon are in this room. If you've seen also younger faces, probably they are students who attended the hackathon and also decided to attend NANOG. The theme of the hackathon was live BGP measurements and monitoring. And I will explain in a few seconds what we mean by that. We had about 90 attendees. 50 of them were competing participants. Out of these 50 competing participants, 30 were graduate students. And we assigned about 33 travel grants, most of them to actual students. Besides that, there were 25 non-competing domain experts, a mix from academia, industry, government agencies, institutions, and so on. So during the hackathon, 15 teams were formed and they competed. This event was jointly organized with the institutions that you see in this slide. Actually, we started working together from November of last year. We collaborated to try to create an ideal environment for the participants to experiment with BGP measurements and monitoring, with live BGP measurements and monitoring. So we made available, we provided both stable and experimental data sources, such as the traditional MRT files that are published by RIPRIS and RouteViews, also streamed by BGP Stream. There was also a Cassandra cluster provided by the group, the BGPmon group at Colorado State University. Live feeds of BGP data through Kafka. The first one was a JSON feed from a new experimental service of RIPRIS, and the BMP data feed from RouteViews, Cisco, and Randy Bush. We also made available the peering testbed from the University of Southern California, which allows experimenters to emulate autonomous systems on the actual internet, and the BGP Stream software framework for monitoring data analysis from CADA, as well as from CADA also Periscope, which is, I have a little bit of feedback, I think, a little bit of echo. Sorry, the Periscope unified interface to Looking Glasses, which is very experimental. And finally, of course, active probing infrastructure, RIPE Atlas, and CADA Archipelago. The participants had free credits for RIPE Atlas, thanks to the RIPE folks. And most of the software was already pre-installed on the compute nodes of the Comet supercomputers. So the participants used actually the compute nodes, each of them has 24 CPUs and plenty of RAM. This event, however, wouldn't have been possible without the support of the sponsors, which we really want to thank. We had large financial support. As I mentioned earlier, we assigned about 33 travel grants from to students that travel from all over the world to participate in the hackathon. Besides that, we had plenty of experts, domain experts. Some of them were from these organizations, and that was great for, in general, for the hackathon. The participants could take advantage of help and support and advice from the domain experts. Indeed, some of them actually sat down with them and hacked and participated very focused on their challenges. Also, we had some jury members that are from these organizations. So every presentation of a hackathon needs to have a picture of the folks locked in the room hacking, and they were really determined. I mean, we had to kick them out at 11 p.m. We didn't stay up for the night. But I have here another slide. Here, Matthew and NANOG kindly posed for this joke. which is just to, to highlight that this hackathon, differently from other hackathons, was not heavily focused on code, but rather on measurement, data analysis, and so on. So, as you know, measurements and internet measurements in particular are kind of tricky. Sometimes the data is not as good as we would like to. Sometimes it's incomplete. Sometimes experiments need to be, measurements need to be redone. And I think this was a good experience for the participants, in particular for the students, to learn more about what are the potential issues in internet measurements and actually learn about the limitations of the state of the art. But I think we can say also that they actually contributed to improving the state of the art. And so here come 4 slides for the 4 awarded projects from 4 teams. Actually, on the website of the hackathon, you find tons of information about the platforms that we use, the documentations of these platforms, the attendees, and of course, each single project that has been carried out during the hackathon. These are really slides put together using the slides of the participants. So the Viz2 team worked on developing a BGPlay installation that is easily deployable. BGPlay, probably most of you are familiar with it. It's a visual interface developed in JavaScript that allows you to keep track, to visualize changes in AES paths towards an autonomous system. So they made it possible to deploy it also in a private installation with that. So this system includes a data collector and supports real-time streaming and visualization. And as you see, there is an advanced diagram that one of the participants created during the hackathon. This project will have a follow-up. It seems that pretty soon they will actually make available either a virtual machine or a system ready to be set up in a private network and to be used also with private data feeds that you don't want to share. The team from the Hijacks2 project instead focused on real-time live detection of BGP hijacking activity. In particular, they've developed a detection system for, again, real-time detection system for MOAS and sub-MOAS events. And they implemented rules to filter out benign cases by using different types of datasets, by using also RPKI, the KDIS relationship dataset, and so on. They made available their source code on the GitHub repository of the hackathon, but most of the participants actually put the code online. The BGP Stream 1 group was made of a single person, Shane Alcock from University of Waikato, and he improved filtering in the BGP Stream software framework. In particular, he developed a BPF-style language for describing filters that can be used both from command line and from the Python and the C APIs. So basically, a user can select which portions of the traffic should be actually processed, analyzed by a BGP Stream application. I think a nice feature that he implemented is the use of regular expressions that can be applied to AES paths. And actually, this project was well received also by the other team participants. They said they would have used these features if they were available during the hackathon. So since this code is pretty close to production quality, probably soon we will integrate it in the next release of BGP Stream. And finally, the Anycast, they are not in any particular order. They were all ranked like the 4 top projects. The Anycast 1 project, in this project, the team used the peering testbed from University of Southern California to emulate a service that uses Anycast. They set up 7 Anycast nodes. Basically, they configure 7 maxes, 7 sites of the peering testbed to announce a chosen prefix. And then they use RIPE Atlas probes to repeatedly trace route to this prefix from different geographic locations. And then they observed the results through trace routes and through the control plane and on the control plane. Basically, at a certain point in their experiment, what they did was to shut down the most popular site, the one that was in Amsterdam, and they observed the impact of these changes. Also, they visualized the impact of these changes by developing a visualization based on the D3 JavaScript software framework. My slides, and here I really want to thank the participants of the hackathon because I think they made it a fantastic event. I think it was very collaborative, very productive, and we hope to repeat it soon. Well, soon. We need some time to recover actually from it, maybe next year. It will follow a formal report, and we know that there are work in progress for blog posts, and we'll post pictures, and there have been some tweets, and you can find, as I said, plenty of information on the website. Thanks. I'm afraid to touch this button. Yes, thank you.
Alrighty, Jeff is going to talk to us about zombies.
Afternoon again. Some talks are informative, some are not. This is one of the latter, and if there's any information contained in this pack, I apologise in advance because it's entirely unintentional. I've talked a number of times about what we actually do to gather measurement, and what we actually do is use an online advertisement. This fetches a number of one-by-one blots. But the problem is that there's so much intercepting middleware. The DNS by design caches stuff. Web proxies cache stuff. Everyone wants to hang on to things and shortcut the answer. But I want to see what you're doing. And the only way I can do that is to make sure that these ads actually load up the system with completely unique URL labels. So we do this around 4 million times a day. So we do a fair deal of just shunting out onto the internet unique labels all the time inside these ads. And so we generate around 12 million DNS queries for these unique names, and we generate around 12 million unique URL fetches per day. You might do the same too. It's just the way the internet works, right? So unique. Unique means exactly what it says. When you have the privilege of getting one of these ads, and for God's sake, don't click on it, the URL inside that ad is just for you. Only you got it. No one else will ever get it. No one else ever got it in the past. It's just you and your single endpoint. The TTL of the DNS, 1 second. So it's kind of, don't learn this crap. It's not worth remembering. The URL fetch, once. So I'm here, and I'm the authoritative name server, and I'm the HTTP thing. I should see you once. Just once. So I get these in my logs. Yeah, right, whoopee-doo. These are date timestamps. So this was collected on the 15th of December, and those are a collection of unique URLs. And just to make sure I knew what I was doing, I put the time of creation as part of the unique string label. And you'll see that time there, I decoded it for you. This is a month old. All of those URLs, all of those unique labels there were actually created around a month ago. It seems there's something weird going on out there, because basically there's an awful lot of zombies going on, that when you ask something of the DNS, it never forgets. And it's really a lot of it. Well, how much of it? Let's just do a graph and apply some science to the problem. What's the age distribution of these zombies? Is it all just, last week, last month? The axis down the bottom is days. 200 days, 300 days, 600 days, 3 years. So when the DNS never forgets, it truly never, ever, 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 ever forgets. That was one server. That's 60,000 hitting one of my servers. The average time, well, if you look at it, that's all the servers, and you start to see that 50% of these zombies are actually 6 months old. What's wrong with you guys? Forget it. Just forget it, right? You don't need to hang on to DNS. It's all crap. Do not remember this stuff. When there's a TTL of 1 second, believe it. That's the time to live. Kill it. No, no. Oh, no. 50% are more than 6 months old, and there's a trailing edge out there at hitting 3 years when I first started doing this. So I look at the number of repeats per day. Some of you are obsessively, compulsively weird. There's one person out there that queries the same dead name 3 times, once every 3 seconds, forever. It's gone. No one ever wants it. Forget it. You look at this distribution and, up the top there, 2/3 of all queries occur only once a day, but the rest of you, no, once is not enough. I'll just keep hammering away. The answer might change. A, the answer will never change, and B, no one bloody wants the answer anyway, right? You didn't need to do this shit. You sort of go, but hang on a second. Is it because you guys run deranged DNS? And you might well run deranged DNS, what do I know? Or in actual fact, it's not the DNS's fault. The DNS is being very nice. You're running deranged web proxies, where the web proxy says that one-by-one GIF, that transparent GIF, is subtly different from all of the other billions of instances of that one-by-one GIF. I need to keep on refreshing that one, yeah? So I thought, well, let's look at the instance of URL zombies. Who knows? It might be the same. There might be a fingerprint here. The web is weird, but differently weird. You notice that age distribution? There's a certain set there that just never, ever, ever forgets, but it's different to the DNS. 50% of URL zombies are only 4 days old. Somehow the URLs, the web caches, have learned the fact that you can forget stuff. It's okay. But the DNS, the obsessive compulsives out there, and you know who you are, just will not forget the DNS. The zombie repeats are different, the patterns are different. So there's something weird about the DNS. Every time you make a query, that query gets placed into the repeat forever bucket. And there's this garbage tip of old DNS queries that we're leaving behind us. And every time your DNS authoritative server is going churn, 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 it's not real demand. Nothing like that. It's just that your resolvers just never, ever, ever forget. But we can use this. I'm applying for a new GTLD name called storage. And the way you write to this is really quite easy. You just ask the same query 100 times and then that's it. The DNS will never ever forget that query. So you put in an index value, which is kind of, how to get it back, and you just write the data as part of the query. Done, right? So once you write it in, how do you read it? Well, you just wait. You just listen and it'll come back to you. Sooner or later that query will come, I remember it now. There's only one minor problem with my idea, however. I can never, ever, ever delete the bloody stuff. Thank you.
So, am I doing this? Okay, hi guys. I'm Mingwei Zhang. I'm from University of Oregon and the Center of Cybersecurity and Privacy. So, in this condition, we'd like to introduce you to our most recent research efforts in terms of defending DDoS. So, this is a collaborative work with my advisor Jun Li and Luming Shi, David Cecilia, Elizabeth Fuller, and our co-advisor Peter Royer from UCLA. So, we have a fancy name called drawbridge, right? We want this project to be really effective as a drawbridge. We command it, and it would level up, and then no traffic should go. Of course, DDoS traffic. So let's go ahead. Of course, we'd like to first thank you, Homeland Security, for funding this project. And so let's talk about problem statement. So we all know DDoS attacks are a serious problem, and we don't need to reinforce this concept anymore. But so DDoS attacks are performed by sending large volume garbage packets, or even seemingly not garbage packets, to their targets. So the problem of the current attacks or their victims are sometimes really small or medium-sized organizations. They don't have these resources to withstand a very large DDoS attack. So some companies seek help from cloud mitigation services, and some companies are trying to just build bigger pipes to withhold the attacks by themselves. However, we look at this problem differently. So when a victim under a DDoS attack, or the end user under a DDoS attack, so the victim should have the perfect knowledge of what is the packets, or what are the packets that they want to have, or what are the packets that they do not want to have. So all the previous solutions, or most of the previous solutions that we know, the DDoS victims just sending a binary signal, 1 or 0, we are under attack, please just help me. But now we want to bring more to the state. We want the victim to be a little bit more knowledgeable about the attacks and tell more to the ISPs that they're working with. So why the ISPs? Why provide more information? That's because the DDoS, the ISPs are the ones that are really able to drop packets or doing something about the attack. If the ISPs are more informed about the attack, and the ISP could do a better job. And also, why ISPs? Because we want this knowledge about the attacks to be propagated to more places, to even further down the road to the attack sources, to where the attack is from. So the question becomes, how do we effectively get this customer's knowledge about the DDoS attack and their needs, their traffic needs, to the ISPs who can actually act on those? So the basic idea of drawbridge is that we want to enable users, end users, of course, the potential victims, to inform the ISPs or ASs who can actually handle the DDoS attack about the DDoS. And we utilize SDN infrastructure to be able to effectively handle those DDoS attacks. So as our prototype implementation, we're using OpenFlow-based software-defined networking. But of course, like all different kinds of software-defined networking is able to filtering any of these attacks. And eventually, drawbridge, our product or research project, we would like to change the chain, we would like to push the change of traffic engineering by incorporating the needs from the users and injecting more knowledge from the users to the ISPs who are doing the traffic engineering. And so drawbridge enables of course, enables the propagation of this DDoS filtering rules from the customer to the ISPs and between the ISPs. So we want this knowledge to be propagated to as far as possible and ultimately stop the traffic if we can, just right outside the attacker sources. So here's an example of how this system that we would like to see works. Of course, it's a simple diagram. So first, the user on the right side, we see here ISP2 are the potential victims ISP, and the victim sit here is a machine that's on the most far right. And this user can subscribe to this drawbridge system or drawbridge service that an ISP can provide or other ISPs can provide. So during the attack, the customer send out traffic or send out traffic filtering rules, which describes what kind of traffic we don't want. So as a simple example, when my personal web server is under like NTP amplification attack, I know for sure that I don't want this type of traffic. I don't need my ISP to run complicated services to learn what type of traffic it should deal with. I just want to tell my ISP, don't do this anymore, just kill all this NTP traffic. So what you will do is that the customer or this end host will send out traffic filtering rules directly to the service provider or drawbridge service provider at its own ISP. And the drawbridge service provider tries to deploy at their own infrastructure, of course. But what if the traffic is too large, like hundreds of gigabytes per second, gigabits per second? So under this large volume of attack, it naturally wants to get some help from others. So what we want to do is that we want to enable this collaboration between ISPs so that this ISP2 or the victim's ISP can call for help, and from ISP1, which they could just act for their customer in terms of ISP or AS, so that the traffic sent from the ISP1 could be also filtered out. So in this case, we enable this collaborative defense not only in terms of the end host and its own provider, but the provider and providers. So the main efforts that we want to push on is that we want to create this chain of communication so that there is a chain of communication can be established. and different ISPs could act together to defend against DDoS attack. So in this project, we're looking at several different aspects inside how can we build this drawbridge system. So the first one is that we need to identify what's the best strategy of forming this collaboration in the first place. We can't just rely on people voluntarily just to join this project and filter our traffic for their customer. It may lose money by doing that, or it may cause other problems, which is naturally a problem to start with. And say we have this collaboration set up, then we also need to discover what's the best locations for deploying filtering rules. Say we have 100 filtering rules. We don't want to deploy at all the ASs on the internet, which is a waste of resources, also could be incur a lot of the economic cost. And we want to optimize the rule space throughout all the drawbridge nodes to reduce the overhead of this DDoS defensing services on their ISPs or on their AS infrastructure, so that it won't incur too much overhead or it won't affect their normal operation. And at last, we want to motivate ISPs to participate. Here, we want to say that participate in drawbridge or run drawbridge service, but we also want to say any of these DDoS or collaborative DDoS attack, DDoS defense solutions, is there any way that we can motivate a collaborative defense scheme that everyone wanted to join? So as a conclusion, there's this project allows the traffic recipients who are hurt by the DDoS attacks can play an active role in responding to them. And they can choose exactly what they want to have and what they do not want to receive. And drawbridge aims to change this, the paradigm of traffic engineering by including those victims' voice into their consideration, and then enable those end hosts and their upstreams ASPs to listen to this request. And at last, we want to establish this collaboration between ISPs, between ASs, in terms of DDoS defense, so that potentially, at the ultimate goal, we want to stop the traffic right from the attack sources. Here, we would like to see what's your opinions about this project and what's your input. And if you have any comments or suggestions, please contact us. And thank you.